today is we'd like to do the local differential geometry of curves. We will try to essentially prove something called fundamental theorem of curves, which is essentially everything about curves in the sense of doing geometry. In order to give some sense that what we are going to talking about, let me begin with an analogy. Imagine you have been blindfolded, okay? So see, what we are doing is all local things actually, because if you see locally things, okay, so when we move on Earth, we feel no curvature. We feel like there is, what do you call, plane line. We're moving in this plane. It's because that there is a very little curvature of this sphere that we are moving on. It's not that much curved actually. It is curved obviously, but it's not that much that we can, really feel it by our, everyday experiment actually. Now, then how we can know that our space is curved? The space on which you are walking, driving, doing something is curved. And one of the trouble with us, with our natural experience, is that we can only observe the things, not too much far. We can only observe a very little chunk of things actually around us. So let me give you an analogy. Imagine you are traveling in a car on a curve actually, okay? But you are not seeing with your eyes are blindfolded with something. Okay? Then how would you know that what is happening? Imagine if your car is going smoothly, okay, you're not feeling any change actually, then what would be your conclusion? Your conclusion is going to be that you are maybe running on something flat. Okay? But imagine, okay, you are feeling that, okay, sometimes you are going up and then going down and then going up and then going down. Okay? Sometimes you are going up with a, very, what do you call, small rate. You're not feeling too much different, but you're feeling that, okay, somehow, the thing is going up actually. And then thing is gradually going down. But what if you feel that, a time comes when you are really sharply going up actually. So you are feeling, that somehow you are basically, mounting over a, kind of a hill actually, okay, through your car. What's going to happen? You will feel basically that, okay, you will feel a curve actually. How about if you are moving on a valley? So you will see that you will have kind of periodic pushes, okay? That sometimes you are going this way and then sometimes you are moving this way. So it's like so this here and there movement can tell you that okay, maybe we are going on some, what do you call, something which is called cylindrical actually. And this is precisely what we wanted to do with our curves. So imagine I have a curve like this. Okay? So if you are on 10, so it's like if you are going on this part, what you're gonna see it? What you're gonna feel? You're gonna feel that okay, your car is somehow going up and then going down actually. So it's a sharp curvature. while like this part is what you call less curved than this part. Are you getting the point? How about this one? So you see, this experiment of, what you call blindfoldingly observing thing is enough to know that. But this is not enough actually, because it can just tell you that, okay, how the curve is behaving in plane. But what if the curve is also twisted in space actually? Okay. So by just traveling along, curve, you're not going to make sense of it. Okay. So you need something else to, make sense that whether you are twisting or not. So the thing that we do is simply, essentially, what? We can just say that, okay, imagine you are a particle and you are traveling on a frame axis. So imagine that's your tangential director, the way car goes. Okay? That's, the direction of the normal. Okay? So it's a plane actually. Okay? It's called the oscillating plane. Okay? E and N. So the movement of this plane is going to tell you essentially that what is the curvature of the curve. And how you can know that whether there are twists in curve or not. Okay, so if you are going flat and you are not getting this kind of feeling actually that okay, you are going in a car but you are not getting twisted actually. Okay, so these twists into the space actually are going to tell you that whether your curve is not only curved but it's also twisted in space. And essentially what we are saying that let's attach a normal vector, binomial vector basically, which is perpendicular to the plane of tangent and normal. Then think about it, it's like this actually. Okay? So when I'm moving on a curve, okay, for example, it's a plane curve for example, then there is no change in binomial. Binomial is changing, you don't see too much change. But imagine I have a wire actually, twisted wire, okay, and I'm traveling on that wire, what's going to happen? So this is going to basically what you call turn and twist, both things. So it's a very natural idea to make sense of curves. And we'll prove essentially something called the fundamental theorem of curves, which is enough actually to know everything about the curves actually. Okay? So this is what essentially we have to do. So this frame, we call it a Frennet frame, is a sufficient thing to know everything about the curve actually and its movement. Okay?
So why isn't the tangential vector enough for determining the curvature?
Because think about it. So it's like the way the tangent vector is changing is going to tell you that how much curve it is. So imagine that I have a circle and I draw a tangent on the circle. So this tangent is constantly going to basically change. So you're going to say that okay, there's lots of curvature here. Okay? While if you see, for example, tangent moving on this part, so it's like on this chunk, so it's not going to be that much change as it is changing in this case. So the change in rate, the at which the tangent is changing, is going to tell you that how does the curve is going on, or how much the curve is, the space is curved actually, or your curve is curved.
Twist the direction binomial.
It's the change in binomial that is going to tell you that how much of the curve is twisted in space. It's a pretty natural idea, you see. So what people have done, they have done nothing, they just took the natural observation and mathematized it. That's it. So let's do. So what we would like to do essentially, we like to talk about Frennet frame. By Frennet frame, I mean this P and B axis, tangent, normal, and by normal vector. So all these are vectors, unit vectors, and we will show that it's an orthonormal basis of R3. Okay. So how to make it? Simple. So imagine that I have a unit speed curve parameterized by its arc length. Okay. Then what would be its derivative at the point beta of s, for example?
Speed.
So this would be not its
Velocity.
speed, it would be the magnitude of it.
Velocity.
But it's the tangent vector. So we find that to be the tangent vector. Okay? That's the tangent vector. We know that beta prime is unit speed, that is, so beta prime is the unit speed. What does it mean? It means that the norm of this is 1. In other words, the norm of the unit tangent vector is 1. In other words, this tangent vector is not just tangent vector, but it's a unit tangent vector. Okay? It's a unit tangent vector. And if it is a unit tangent vector, you can say that this satisfies this equality that if you take the dot product of tangent vector, everything is depending on s. Okay? With itself, what you're gonna get? You're gonna get 1. Are you getting it? Okay. Now, as we saw, or as we kind of understood through our intuition, that it's the change in the tangent vector is going to tell you, okay, the curvature, or maybe from that we can fetch the notion of curvature. So in order to get the change in the tangent vector, what we need to do?
Derivative.
We need to differentiate.
Differentiate.
So if you differentiate this one times with respect to s, what you're going to get? So apply the product rule, so you're going to get t prime, t, and t prime equal to 0.
2
So
times.
you're going to get t 2 times, okay, so you're going to get 2 times the t prime of s dot t of s equal to 0. That is, what did you get? You get t prime of s dot t of s equal to 0. Okay? So these are some of the key observations that I would like to point out. Are you getting the point? So what does this guy show? This shows that t prime is orthogonal to t of s actually. Okay? But on curve, at a point, if I am drawing t of s, there is another thing which is orthogonal to the curve actually, and that is normal vector. Okay? There will be a normal vector. Are you getting the point? So if this guy is orthogonal to t of s, okay, and t prime is also orthogonal to t of s, then somehow normal and t prime of s must be parallel to each other.
Yes.
Okay? Must be parallel to each other. So it would be something like this situation. Something like this situation. Are you getting the point? And if two vectors are parallel to each other, how we can relate them?
By some constant.
By some constant. So you're going to say that, okay, if this is a vector A, this is vector B, then this A is some constant times B. Okay?
So why can't they all be perpendicular to each other?
What do you mean by that?
Why can't it be perpendicular to a normal vector?
No, I mean, you're saying that, okay, something that is perpendicular to binomial, but, this can't happen, think about it, okay? Whenever, even in calculus you do this actually, okay? That whenever you are talking, so you're saying that why this perpendicular thing, okay, is is not perpendicular out actually, so it's like that, yeah? Not in the direction of the binomial. But it's going to assume an unnecessary thing that the binomial is at the moment orthogonal to normal. Therefore, we don't know actually. So how can I say that? You know, this is perpendicular to this. Are you getting the point? Okay. So this is simple vector calculus thing that if you have a tangent vector, okay, and you know you want to compute its derivative, you will get a normal vector, okay, but in kind of inward direction of the curve. Okay, something pretty simple. Are you getting the point? There is another way to, do the thing. So one way is that you can say that from this it follows that T prime and N of S must be, parallel to each other, and hence we can find some K of S, okay? So some quantity depending on S, such that I can say that T prime of S is equal to K of S times N of S. Something like that. Okay. There is another way you can reach to the precisely same equation. Think about it. What if, so T prime of S is telling me what? It's telling me that how the tangent is locally changing on the curve. And if I define this quantity to be K of S, so one way is this, but I can also do this, that the magnitude of the change in the tangent vector of S, the amount of the change that is taking place in the change in the tangent vector, we call this as the K of S, or called the curvature. That's your curvature. So curvature is what, essentially? So it's how the tangent vector is changing on the curve. Okay? So the way tangent vector is changing on curve is going to be
Acceleration, nothing is there. Acceleration.
No, it will not be acceleration. Acceleration would be something depending on it, but it would not be acceleration actually.
Sir, because tangent gives us velocity, and we are differentiating basically velocity once. So, sort of acceleration.
No, we will write an explicit expression, of acceleration in the terms of tangent. So we'll see that this is not sufficient. Okay, so acceleration is going to have two components actually. So one is tangential component, which is going to be this K of S, but it's going to also have a normal component. Okay. So one way is that you can say that since T prime is of S is parallel to N of S, so there exists K of S such that like this. But the other way is this. In some places you will find that let's give K of S as a name of what do you call T prime of S. Okay? And define the normal of S rather than assuming that normal vector exists. So define normal of S as a vector T prime of S divided by the magnitude of T prime of S. So it's like a unit vector, in the direction of the change in the T prime of S. Okay, and from this you again reach to the same quantity. Let's think about it. Okay, so either you can define the way you want to define, or you can do things in this way. Are you getting the point? The key difference here is going to be that if you are taking this treatment, then your K of S must be always positive. Okay? It must be positive. Are you getting the point? Is it making sense? So what is the key relation then? The key relation is this. Okay? And what this quantity K of S is, okay? So from this you can also compute K of S actually, that if you take the magnitude on both sides, okay, then K of S is like a scalar, and the magnitude of S and normal vector is 1. So the K of S is going to equal to, the T prime of S actually. Okay. So this quantity K of S is called the curvature of the curve. Okay? And really, the curvature is the key topic of this course. So we want to understand curvature. That's it. That's what we want to understand. Nothing else. Okay? So from the day 1 to the day last time, we want to understand curvature. For curves, for surfaces, for manifolds, that's what we want to do. Okay, are you getting the point? So what does the curvature is going to give you? Is going to give you the rate by which the tangent vector is changing on the curve. Okay? Or you can also treat this as that, imagine you have a fictitious line, then how much of the curve is deviating from this fixed straight line. So that is what the quantity K of S is going to tell you. That how much of your curve is deviating from what we call essentially straight line. Anyway, is it making sense? Okay. So you want to compute the curvature? Pretty simple. What you need to do, differentiate your unit speed curve and compute its magnitude. You're going to get curvature. That's it. What do you mean by curvature? So we are interested in the positive curvatures, but if the curvature, here's something pretty intuitive. If the curvature is 0, on what thing you are, traveling? Plane or straight line actually. So in case of the curve, you are, you are moving on a straight line. So you are not doing something interesting actually.
So from
So the only interesting thing is going to be that when curvature is a positive.
From this definition, it seems it can never be negative.
Yes.
The way
But
we
this is what essentially we're going to assume that, okay, the curves don't have negative curvatures. You can define it, but okay, there is no need to get into that much complication there. We're going to say that either curvature is 0 or positive. That's it. Okay, the next is that now we have our two vectors. So we have tangent vector and the normal vector. Take their cross product. So T cross of S and N cross of S. So what are you going to get? You're going to get another vector which is perpendicular to the plane of both. Okay? And let's denote this by V of S. And call this vector as binomial vector. So binomial vector is what is a kind of a vector. It's going to tell you which is perpendicular to the plane of both, tangent and normal. Okay? Is it making sense? Why this vector is responsive? So now essentially what you have a frame actually on, which is kind of moving on the curve. Okay? So the change in T is going to tell you that how much the curve is curved, and the change in V of S is going to tell you, okay, that how much of the curve is in space actually. Imagine if this curve is not in space, then what's going to happen? This V of S is going to be like a constant actually. It doesn't have any change. Okay? But if the curve is twisted in space, then there is going to be essentially change depending on the kind of curve you have. Yes, you can take this. You can have this, what do you call, the better is to use this. And you have this, what do you call, a frame attached to it. So, when you're going to move on this, imagine that, the direction of the curve is going to change actually. Not only the direction of this binomial is going to change, but it's going to, depending on that, what kind of place you are moving on. Okay? So it's pretty natural idea, it's a very natural idea. So next, obviously, as we kind of saw that B prime or B is going to give us a good information about curve, that how much of curve is twisted in space, then obviously we'll be interested in its derivative actually. And let's see that its derivative depends on what. Okay. One of the obvious things that we can have actually is this actually, that all these three vectors are unit vectors. So they satisfy this, that T dot T and B dot, just like N dot N and B dot B equal to 1 actually. So their magnitudes are 1. And they are orthogonal to each other. T dot N and T dot B and B dot N they're all orthogonal to each other. So these are what you call the immediate properties of this what do you call T and B are. And this helps us to, this is going to help us to, compute the change in B prime, the binomial. How can I compute it? So take any relationship, for example, take this one, okay, because if you differentiate it, you will have T prime and B prime involved. So we already know that what is T prime. So we can come up with some conclusion. Okay. So if the T dot B is 0, and if you compute the prime of it, what you're gonna get? So you're gonna get T prime dot B plus B prime dot T equal to 0. Okay? But
B prime is T.
B prime and T prime is what?
T prime is K
Uh-huh.
plus N.
Okay? So T prime B is what? So I can take, okay? So I have B prime dot T plus T prime, which is
K time.
K times,
N of S.
okay?
K of S, N of S.
K of S, okay, K of S, N of S, already Kn, Kn dot
B.
B equal to 0. But you know something interesting here, that B dot N is 0. So what did you get is that B prime
T is equal.
is 0 actually. Okay? So you get that B prime dot T is 0.
But closing कर रहे हैं ना B dot N को 0.
Assume नहीं कर रहे, we are saying that okay, they are indeed orthogonal to each other. That's what the definition is telling you.
We are splitting K as scalar.
Huh?
There we are splitting K as scalar.
K is in a scalar quantity
But
because it's a magnitude.
K is to depend on S.
Depending on S, that everything is depending on S. I can write it in this way. Okay, so it's just a scalar quantity. Okay. So you got this. So what follows from here is that B prime of T is orthogonal to T. So it's orthogonal to T. And another interesting thing, the same, okay, how about, okay, so that's one conclusion, keep it in your bucket, okay. How about if I take this identity now, B dot B equal to 1, and I differentiate it the way I differentiated T. So I'm going to get B prime dot B is 0. So what did you got? You got B prime is orthogonal to B and B prime is orthogonal to T. So where is going to be B prime?
in
So it must be something parallel to